Assalamualaikum and hello to everyone. Today we will present about bipolar junction transistor, or the short form is BJT. This presentation will be presented by our team. This presentation will start from me, Muhammad Asad Al-Basri bin Muhammad Noor, and followed by Muhammad Arif bin Kamal, Dennis Farhan bin Hazrul Fazli, and end by Muhammad Shafiq bin Wan Abdul Malik. First, we will explain about type, basic instruction, symbol and operation of BJT. Second, we will explain about the construction and characteristic of BJT in terms of different type of instruction. And lastly, we will explain about one calculation example of any BJT configuration. They have two types of BJT, that is NPN and PNP. Let's see NPN first. First, we need to know what is VBE, VCE and VCB. VBE is voltage between base and emitter. Then VCE is voltage between collector and emitter. And VCB is voltage between collector and base. The current flow will start from the collector through base then into emitter. Then VCE is supply voltage with respect to emitter, and we need to remember that collector is always more positive than base and emitter. Then they have second type, that is PNP. VBE of PNP type is negative at base terminal and positive at emitter terminal. The base terminal is always biased negative with respect to emitter. The VCE of PNP type is emitter supply voltage with respect to emitter, and we need to remember that emitter is always more positive than collector and base. For the basic structure, we can see NPN type current flow based on the arrow that start from the collector, and for PNP type, the current flow start from emitter. But in exam, we don't use basic structure, but we use symbol for the circuit. We can identify the type of BJT from the arrow on it. We can see the PNP type, the arrow facing the base, and for NPN type, the arrow facing the emitter. The arrow shows us the current flow of the BJT.
For operation of NPN, base emitter in forward bias, base collector in reverse bias, the electron to be injected from emitter into base. This allows whole positive charge carry flow from to emitter to base. So, the layer wide at EB junction is reduced. The collector base junction widen the depletion resistance and prevent the majority carry of electron. The transistor acts as amplifier, with the collector current being controlled by the base current, so the layer wide at CB junction is increased. The current flow from the collector to the emitter. For operation of PNP, base emitter in forward bias, base collector in reverse bias, electron to be injected from emitter into base. This allows electronegative charge carry to flow from the emitter to base, so the layer wide at EB junction is reduced. The collector base junction widen the depletion resistance and prevent the majority carry of electron. The transistor acts as an amplifier, with the collector current being controlled by the base current, so the layer wide at CB junction is increased. The current flow from the emitter to the collector. Construction of BJT. For PNP construction, in PNP bipolar transistor, the N-type semiconductor sandwiched between two p-type semiconductor. PNP transistor can be formed by connecting cathode of two diodes. The cathode of the diode are connected together at a common point known as base, while the anode of the diode that are on the opposite side are known as the collector and the emitter. The emitter base junction is forward bias, while collector base junction is reverse bias. So in PNP type, current flow from emitter to collector. The emitter in this case is at high potential to both collector and base. Construction of BJT. For NPN construction, NPN will differ with PNP type. In NPN, the P-type is sandwiched with two N-type. When two diodes are not connected, it forms NPN transistor. The current will flow at collector to emitter. It happens because collector terminal more positive than emitter. In case of NPN collector, the arrow mark is outward, which show the flow of current from collector to emitter.
As we know, in the transistor there is base, emitter and collector, so the transistor can be functioned as it should be. And we should know that each of it has its own characteristic. For the first graph, It shows input characteristic graph depict the relationship between IB and VBE for the input in a common base. We can see that when VBE increase, IB generally also increase, but the curve may exhibit saturation or other nonlinear behavior at higher voltage. Meanwhile, for the output, we see that it has different characteristics. From the output graph shows the relationship between IC and VCE. It shows that where IC is relatively constant despite variation in VCE. And next is for the common emitter. The input characteristic shows relationship between IB and VBE. As VBE increase, IB generally follows the displaying a somewhat linear relationship. And for the output graph, it shows relationship between the IC and the VCE. This linearity arises due to the fact that emitter is directly connected to the ground, providing a straightforward relationship between IE and VE. Lastly, for the common collector. The common collector configuration is used primarily for the independent matching purpose, since it has a high input dependence and low output dependence. It's different from the common base and the common emitter. And for the input characteristic graph, it typically shows a relationship between the IB and VBE. The shape of this graph is similar to that of the common base configuration, reflecting the common collector's low input dependence. And for the output characteristic graph, it illustrates the relationship between the IC and VCE. We can see that the constant IC over a range of VCE in the input indicates the configuration is relatively stable regarding change in the collector to emitter voltage.
Okay, so now I want to explain the calculation example for the BJT configuration. For this example, the question has a circuit and asks us to find IB, IC, VCE and VBE. In this question, the value of beta has been given, which is 150. So, to find IB, we can use the Kirchhoff voltage law KVL, which is total voltage is equal to 0 in loop 1 of the following circuit. And the calculation is VBB minus IB times RB minus VBE equal to 0. We use IB times RB because we use the Ohm law that V is equal to IR, and we use I times R to get I. Then we find IB by calculating IB equal to VBB minus VBE divided by RB. Then entering the value 5 volt minus 0.7 volt divided by 10 kilo ohm. As we know, the value for VBE is indeed 0.7 volt, and the answer for IB is 430 microamperes. To find IC, we use the formula IC equal to beta times IB and enter the value 150 times 430 microamperes. We will get 64.5 milliamperes for IC. To find VCE, we use KVL just like looking for IB before, but in the second loop. The calculation is VCC minus IC times RC minus VCE equal to 0. Next, enter the value 10 volt minus 64.5 milliamperes times 100 ohms, and the answer for VCE is 3.55 volt. Last but not least, to find VCB, VCB is equal to VCE minus VBE. Enter the value 3.55 minus 0.7, and the answer for VCB is 2.85 volt.